Students, we will discuss about wideband pass filter in the last class. In the wideband pass filter, we are connected the high pass filter and the low pass filter in the cascaded form to filter out the frequencies from to pass the frequencies from 200 hertz to 2 kilohertz. So it means the wideband pass filter will pass the input frequencies from input side to the output side only between the band of frequency between 200 hertz to 2 kilohertz, because this will be achieved by the first order high pass filter section as well as the first order low pass filter section, because we need the waveform in such a way that is the roll of rate, because at the starting it should not pass any frequency signals from 0 to FL, and similarly from FL to FH, that is the wideband pass filter should pass all the frequency signals from input side to output side, that is during it is called as the bandwidth. Why it is called as the bandwidth means from the lower frequency signals to the higher frequency signals, it is passing the frequencies. Therefore, FH minus FL is the bandwidth. And also after the high frequency signals, that is the band pass filter should not pass any signals, and from there onwards the frequency signals will start rolling off, or it will decreases, or it will stop the passing of input frequency signals to output, and the roll off rate is minus 20 decibels per decade, and this will be achieved in the by connecting the high pass filter cascaded with the low pass filter sections. In the previous class, we have discussed, once you refer the notes, and on this one, we will discuss about the problem. The problem on this one is, there is the problem on the wide band pass filter. Here we have to design the band pass filter. Design a wide band pass filter having the low frequency signal. FL is lower cutoff frequency is 400 Hz and FH is 2 kilohertz, and pass band gain. The pass band gain is AFT. That is, the total pass band gain is 4. Draw the frequency response of the filter and also calculate the Q, that is the quality factor of the quality Q value of the filter. Here we will discuss the design, how to design. What are the things we have to design? The values of the low pass filter, the values of the high pass filter. That is, the various values we are discussed in the previous test section. These values we have to design. What are the values we have to design in the circuit? I will show the circuit, the values in the high pass filter is R1, RF, capacitor, the resistor. In case of the high pass filter section, similarly R1 dash, RF dash, R dash, and as well as the C dash in case of the low pass filter section. These values we have to calculate in the problem. That is, first we will discuss the second section of the designing of the second section. That is the low pass filter section. That is the low pass filter section. That is, we have to, it will pass the lower frequency signals and cut off the high frequency signals. That's why the higher cutoff frequency is 2 kilohertz. It means the low pass filter pass all the frequencies from low frequency signal till 2 kilohertz. That's why FH is higher cutoff frequency is 2 kilohertz, and assume its C dash is 0.01 microfarad. I am assuming C dash of lower cutoff frequency section, low cutoff frequency section as 0.01 microfarad. As we know, FH is equal to 1 by 2 pi R dash into C dash. That is R dash into C dash. Therefore, R dash is equal to that is 1 by 2 pi R dash is given, that is we are taken, that is R dash is equal to 1 by 2 pi FC. Actually, we are going to take R dash is equal to 1 by 2 pi FH into C. Therefore, 1 by 2 pi FH is 2 kilohertz, and C dash value we are assumed that is the 0.01 microfarads. Therefore, I am getting this R dash value of the low pass filter section is 7.957 kilo ohms. As we know from this one, we know here we already know the value of, we have assumed the C dash, we have calculated the R dash value. Then calculate the value of the R and C value of the high pass filter section. Design of high pass filter section. That is, lower cutoff frequency is 400 Hz. From 400 Hz onwards, it will passing the frequency signal till from 0 Hz to 400 Hz. It will not pass any frequency signals, and from 400 Hz onwards, the high pass filter will pass the signal. Therefore, I am assuming C value is 0.05 microfarads. Why I am assuming that is capacitor values 0.05 microfarads means that is the frequency is 5 times higher, cutoff frequency is 5 times more than the high pass section, that is 5 times more than 5 times. That's why I am multiplying the capacitor value with 5. That is 5 into 0.01. I am getting, that is C is equal to 0.05 microfarads, because 5 into 4 jar, that is 5 into 4 jar means that is we are getting to get the 2 kilohertz. Okay, that's why I am going to take the capacitor value of high pass filter section as 0.05 microfarads, and similarly I am going to calculate Fn is equal to 1 by 2 pi RC. That is, as we know, the formula, standard formula. From this I am going to calculate the value of R, because we assumed the value of capacitor, and we know the value of the lower cutoff frequency. From these two values, I am going to calculate the value of R in the high pass filter section. From this one, 1 divided by 2 pi into FL is 400 Hertz into C is 0.05 into 10 raised to minus 6. From this one, I am going to get the R value is 7.95. R dash value is 7.95 and R value is 7.95. Now, the total pass band gain is equal to A1 into A2, where A1 is equal to the gain of high pass section, that is the first amplifier and the high pass filter section, that is the second. A2 is the gain of the low pass filter section. Here already given in the problem, the total pass band gain is 4. Total pass band gain is 4. Therefore, let I am going to assume A1 and A2, both A1 and A2 is equal to 2. That is 2 into 2, that is the total we are going to get 4. Now, for non-inverting operational amplifier is the gain, the total gain is the gain of the amplifier. Each amplifier is A1, A1 is equal to A2 because A1 both are equal. That's why for the non-inverting amplifier, operational amplifier, the gain is 1 plus RF divided by R1 is equal to 2. Because I am going to take the values of A1 and A2 both are same. That is, I am going to calculate the value of RF and R1 in case of high pass filter section, and in case of low pass filter section, RF dash and R1 dash, because both are same, because the gain A1 and A2 are same. That is, A1 is equal to A2 is equal to 2. That's why I am taken A1 is equal to A2 is equal to 1 plus RF divided by R1 or 1 plus RF dash divided by R1 dash in case of low pass filter section. That is, therefore RF is equal to R1. That is, RF is equal to R1 for both the sections. That's why I am going to get RF is equal to R1. I am going to assume RF is equal to R1. That is, RF is equal to R1 is equal to 10 kilo ohms. I am going to assume here RF and R1 in case of high pass filter section as well as low pass filter section. That's why I am going to get in the high pass filter. I am going to draw once again the circuit diagram of high pass filter section and as well as the low pass filter section. This is the high pass filter section and this is the low pass filter section. Then I'm going to indicate the values. That is high pass filter section capacitor value. I am assumed R value we are calculated. Its value is 7.95 kilo ohms and RF is equal to R1. I am assumed that is RF is equal to R1 is equal to 10 kilo ohms. That's why. And also RF dash, actually it is RF dash and R1 dash is also 10 kilo ohms in case of low pass filter section. To obtain the frequency response of the following equations, which is the magnitude of the voltage gain of wide band pass filter, we are going to take, that is the magnitude of the wide band pass filter is equal to magnitude of the voltage gain of wide band pass filter is, that is as we are calculated in the previous section, AFT into F divided by FL divided by square root of 1 plus F divided by FL whole square plus into 1 plus F divided by FH whole square. That is the magnitude we are already calculated while I am explained this one in the previous section already, because both are in cascaded. That's why I am going to multiply the magnitude of the low pass filter section and magnitude of the voltage gain of high pass filter section. I am getting the magnitude of the voltage gain of wide band pass filter. That too, it is, if it is a first order, it is a first order wide band pass filter. If it is a second order, it is a second order filters. If I am cascaded, it is a second order wide band pass filter. That's why I am taken the total magnitude of the voltage gain of wide band pass filter. This is the total magnitude of the voltage gain of wideband pass filter. From this one, we are going to calculate by selecting the frequencies and tabulate the data for frequency response. Then I'm going to assume in the first column 10 Hz, 100 Hz, 400 Hz, 1000 Hz, 2000 Hz, 5000 Hz, and 10,000 Hz. Next, I am going to getting the value of magnitude of the voltage gain of wideband pass filter. That is, here I am going to get, if I am going to put the value 10 kilohertz, that is that F is 10 hertz, F is 10 hertz. In the above equation, if I am going to take F as 10 hertz, here also F as 10 hertz, and here also F as 10 hertz. Already we know the values of FL and FH. FL is 400 hertz and FH is 2 kilohertz. By putting those values, and AFT is how much? AFT is 4, not 2. AFT is 4. By putting all the values, I am going to calculate here the value of the magnitude of the transfer of magnitude of the voltage gain of the wideband pass filter. That is the second column for the corresponding value of frequency, input frequency signal 10 Hz. That is the value of that one. I'm going to get 0.0999, and similarly I'm going to describe that one in the form of decibels. That is, to get the value in decibel form, I'm going to take 20 log to the base 10 of this value. I'm going to get the value of this one, decibels. And similarly for input frequency of 100 Hz, the magnitude of the voltage gain I'm going to get is this value, and in terms of decibels I'm going to get minus 0.27 decibels. If I am going to take, because it will start from 400 Hz, that is the magnitude of the voltage gain of the wideband pass filter is 2.77. It is nearly equal to 3, that is equal to 3. Then the magnitude of the voltage gain in terms of decibels is 8.86. 8.86. Next, and after 1000 hertz, for 1000 hertz, the magnitude of the voltage gain of the wideband pass filter is 3.32, and its value is 10.42. 10.42. And if the value is again at 2000 hertz, automatically it will drops by 3. Nearly it will drops by from, it will be increases and becomes constant till 2000. At 2000 it will drops by 3 decibels. Between these three values, you see from 400 hertz it will go on increasing. It will becomes constant at that particular value 1000. At it will be up to 2000, up to 2000 it will be constant. If it is nearly going to nearly equal to 2000, it will drops by 3 decibels, increases by 3 decibels. It becomes constant during from 400 hertz to 2000 hertz. At 2000 hertz it will be drops by nearly 3 decibels, nearly 3 decibels. That's why we are seeing the same frequency response as we are drawn earlier. Next, as I'm go on increasing, because after 2000 hertz of input frequency, it will goes on drops, going to drop at 5000 hertz. It will be nearly 3.41 decibels, and at 10,000 hertz the voltage gain is 0.783, because almost all, that is the frequency will be not passing from input signal to output signal, and its decibel value is almost negative. That's why as the frequency rises above higher cutoff frequency, that is the voltage gain will goes on decreases, and also in terms of decibels it is also decreases. Therefore, if the voltage gain decreases, automatically the input signals will not transfer from input side to the output side. That's why it goes on at one time, it becomes very negligible, or it is equal to the zero, because all the input signals after 2000 hertz are 2 kilohertz. After 2 kilohertz, that is a higher cutoff frequency, all the frequencies will be cut down after 2 kilohertz. That is, this will be drawn by taking at y-axis, we are going to take the voltage gain in terms of decibels across y-axis, and frequency, input frequency along x-axis. We are going to draw it in the similar graph, and we can draw it that one by for the corresponding values of in terms of decibel values across y-axis, and x-axis to take these values, and we are going to draw, we are going to get the same frequency response as we are seeing in the previous sections. Okay, the same type of things we are seeing the cutoff frequency. Just you see here, that is the cutoff frequency, that is the uh, higher cutoff frequency. There is the cutoff frequency is the whenever fc is equal to square root of fl into fh. Fl is the lower cutoff frequency, and uh, fh is the higher cutoff frequency. That is the critical frequency is, there is a frequency at which the gain is maximum. We are going to calculate the critical frequency is the square root of fl into fh. That is square root of 400 into 2000. We are going to get 8,894.4. That is nearly 895. That is hertz. At 895 hertz, the critical frequency, the gain is magnitude. The gain is magnitude. Total pass band gain is magnitude at this frequency signal. One more problem, I am going to assign this one as the, there is design. One more problem is design a wideband pass filter with FL is equal to 200 Hz and FH is equal to 1 kilohertz. In a similar way, and a pass band gain is 4. And a pass band gain is 4. He is asked here again, we have to design, what are the points we have to design? One is in the higher cutoff frequency section, we have to calculate capacitor value, resistor value, C, R, RF and R1. In the lower cutoff frequency section, we have to calculate the R dash, C dash, RF dash and R1 dash. We have to calculate these values, and we have to draw the frequency response. He is asked to calculate and draw the frequency response, and also is asked to calculate the value of the Q value. There is a Q value. He is asked the Q value of the quality factor of the filter. In the low pass filter section, there is higher cut. Its higher cutoff frequency is, in the problem is given, fH is equal to 1 kilohertz, and I am assuming here again the C dash is 0.01 microfarad. Therefore, from this one, fH is equal to, as we know, that is the equation 1 by 2 pi R dash into C dash. Already we are calculated and we are discussed how we got this equation. Then R dash is equal to 1 divided by 2 pi fH into C dash. Therefore, 1 divided by 2 pi. fh is 1 kilohertz, 1 into 10 raised to 3 into c dash is 0.01 into 10 raised to minus 6. I'm going to get the r dash value is final value, that is 15.9 kilo ohms. Since the band pass gain is 4, the gain of high pass as well as low pass sections could be set equal to 2, because the high pass sections and the low pass sections we are going to set, that is A1 and A1 is equal to A2 is equal to 2. That is, the input and feedback resistors must be equal in value. Say that is RF and R1 is equal to 10 kilo ohms, and RF dash and R1 dash both are 10 kilo ohms. That is, we are selected the RF and R1, RF dash and R1 dash in the high pass section as well as low pass section. Next, the voltage gain magnitude. Here we are calculating the voltage gain magnitude of the band pass filter is equal to the product of the voltage gain magnitude of the high pass section and the low pass filters section. Therefore, the V0 divided by the magnitude of the voltage gain of the wide band pass filter is equal to as AFT into same F divided by FL divided by square root of 1 plus F divided by FL whole square into 1 plus F divided by FH whole square. And same AFT is equal to total pass band gain, F is equal to frequency of input signal, and FL is equal to low cutoff frequency, and FH is equal to high cutoff frequency. Here AFT is equal to 4, FL is equal to 200 Hz, and FH is equal to 1 kilohertz. Then the frequency response data are obtained by substituting into the above equation the values of F, the input frequencies taken from 10 Hz to 10 kilohertz. That is at the first column, 10 Hz to 10 kilohertz. Then I am going to calculate the gain magnitude of the filter is equal to V naught divided by Vi. I am going to calculate from the above equation. I am going to get the first 10 Hz. I am going to get this value, and the corresponding value magnitude of the voltage gain magnitude is, I am going to get 20 log to the base 10 V0 divided by Vi. That is 20 log to the base 10 0.1997. I am going to get minus 13.99. Similarly, for the 30 Hz input frequency, the gain magnitude of the filter I am going to get 0.5931, and similarly, if I am going to get the magnitude in decibels, I am going to take 20 log to the base 10 0.5931. I am going to get minus 4.54. That is, the frequency will be starting from, that is, the lower cutoff frequency in this case is, the lower cutoff frequency FL is in this case is given the lower cutoff frequency, that is 200 Hz, 200 Hz to 1 kilohertz. Similarly, you see from 200 Hz, that is its value in gain magnitude value of the filter is 2.774, and its value is in terms of decibels is 8.861. And similarly, for other frequency, that is 447.2, I am going to get 3.43.33, and its value is 10.446. At 700 Hz, its value is 3.151 and this value is 9.969. At 1000 hertz its value is again 2.774 and its value is 8.867. That is between this one it will be rises and from this value it becomes from 0.707 AFT and become 3 decibels rises and it becomes constant at the particular value from 200 hertz to 1000 hertz. It becomes constant at 1000 hertz. It will becomes 3 decibels down or rolls off at the rate of minus 20 decibels per decade. Here it will be rolls off at the rate of plus 20 decibels per decade from the 200 hertz. This 20 decibels plus 20 decibels per decade means for every and that is 100 10 times frequency increase in 10 times frequency it will be increases by plus 20 decibels. Therefore it will be increases in terms of decibels. I am seeing that is by plus 20 decibels per decade. That is why I am going to show the values of 5.66 and also again at 100 hertz, 1000 hertz, it is again 8.86. Both the levels are same. After the higher cutoff frequency, the value will be go on decreasing or the magnitude gain magnitude also decreases. It means after higher cutoff frequency, the gain will go on decreases and the input frequency will be not allowed to pass from input side to output side. That's why it will be allowing the frequency band of frequencies from 100 200 hertz to will be allowing the band of frequencies from 200 hertz to 1 kilohertz or 1000 hertz. That is the range will be passing from the frequencies from here. That is the whatever I am given the values will be passing, that is the corresponding values of the magnitude of gain magnitude in decibels and the corresponding values of the gain magnitude in terms of decibels. That is the difference whatever will be raises by 3 decibels and here also it will be raises by 3 decibels and becomes decreases by 3 decibels and below between 200 hertz and 1000 hertz all the frequency band of frequencies will be passed from input side to output side without any attenuation. We will see the diagram. We will see the diagram. That is I am drawn across y-axis. I am taken the magnitude of the gain of the filter across y-axis and the input frequency across x-axis. And here I am taken 10 hertz, 100, 200 cutoff frequency and FH 1 kilohertz higher cutoff frequency and 10,000 hertz or 10 kilohertz. Here I am taken minus 15 decibels, minus 13.99 decibels. Next, minus 10 decibels, minus 5 decibels, minus 4.57 decibels. Because the wherever the points, I'm going to get the values, the corresponding values. I'm taken those values. I'm indicated here. Next, plus 10.46 decibels. I'm taken all the values I've drawn from 200 hertz to 1 kilohertz. That is from 200 hertz from this point to this point. It will be we are going to get the all the frequencies will be passed easily without any attenuation. from 200 hertz to 1 kilohertz. It will be passing easily. After this point, it will be decreases by minus 20 decibels per decade. And after this point, from this point, it will be increases from this point to this point. It is increases by plus 20 decibels per decade. That is the difference how we are going to calculate. And this FC is why we are going to take this values, because at this point after drawing the frequency response in graph sheet, we are going to find out FC value, critical frequency value, at which the gain is higher. The gain is maximum. The gain is maximum is at 10.46, and the gain magnitude is higher. That is for that one. What is the frequency? Frequency is 447 hertz. This is the critical frequency at which we are going to find first the gain is magnitude, and the corresponding frequency we are going to find out. Okay, that is the way how we are going to find out the critical frequency for the maximum total passband gain. Then critical frequency is easily possible to find out. That is the critical frequency is square root of fh into fl. That automatically we are going to find out 447.2. From this one we are going to find out also we have to get the frequency response in the same format. The same format we got, and the corresponding critical frequency value we got. That's why that is any queries related to these two problems you can ask through WhatsApp or send any queries related to these two problems. Thank you.